Gentlemen, I hope I find you well. I had a recent conversation through an email with a gentleman who was aspiring to be an API inspector who lamented the difficulty of identifying different types of pressure vessels. And what I was trying to explain to him was there are ways, especially for exchangers, that coincide with the diagrams that are found in API 572 that are the TEMA exchanger component types as it relates to the letter designations. And I wanted to go over that with y'all in a video today to help explain to him, and hopefully others, there is an established method that makes it easy to describe heat exchangers. And I wanted to go over those with you. What we have here is the figure A12 from the 572, which is a copy of the TEMA exchanger head types and shell types. The front end head types, the shell types, and the rear head types. And these, combined with the legend of the components, yields us these examples. And these are examples directly from the 572 that coincide with the TEMA lettered designations. So this is shown as a AES, an Alpha Echo Sierra heat exchanger. And from the configuration type, that tells us that that is an A-type channel, one that has a removable front cover and a removable flange betwixt the tube sheet and the front side channel flange, has an E style, a one pass shell type, and an S floating head, an S type floating head. And there are many examples from the different types on the front, but what we need to realize is that most of the heat exchangers we'll see are either an A through C, an E through F, and a S, T, or U type bundle. Let's go back to the example. So an AES, the bundle has a S-style floating head. Now, when I talk to people about this, they quickly find out that I'm a geek about all things code, but I want to go over that it's actually fairly easy to tell the difference in the different types of floating heads versus a U-style bundle, a U-style rear head. So here we have an example of a CFU. What's the difference between a C and an A? Well, at first glance, they're both channels, but here's an A and here's a C. The difference is that the rear flange / tube sheet is integral to the channel. So on a C, it's connected, and on an A, it's awesome because it separates. So that's the difference between an A and a C. And the difference between a U, a P, an S, and a T is that P stands for packing. There is a packing material back here. A U is a U-bend on the bundle. And what's the difference between an S and a T? Let's look at this example. An S, in order for the bundle to come out of the shell, it has to be disassembled. Easy way to remember that, S stands for stuck inside the shell until disassembly. A T can be taken out, still assembled. Quite literally, a T letter designation for the rear cover means that you do not need to disassemble the floating head to pull the bundle portion of the components. Real easy way for someone to look at something that's in the field and to be able to use just the letter designations to describe all the component assemblies. This is a really good way to very quickly be able to uniformly be able to describe in both your notes and a report heat exchanger. And just as is done in the TEMA, we describe all exchangers by the nominal diameter rounded to the closest integer in both diameter and in length. And lengths are measured from the flange face to flange face, tube length. And on a U bend, a U bundle, they're measured to the tangent line of the bend. So this area here is not included in the total length of the tubes. Another good way to describe things, here's another example. Here's the AKT. So once again, we have an A style channel, K kettle shell, and T. If it's in a kettle, it's almost always going to be a T, a tango style floating head, because in order to get this out, it has to be able to be taken out without being disassembled. If it was an S, the only way to get in here and get this bundle out would have a manway opening or a removable portion back here where you could get in here between the weir and the floating head to disassemble this while it was still in place. That would obviously not be a very good scenario either for construction or for maintenance and further repair. So as a result, any kettle boiler will have either a U or a T style bundle. I guess you could have a couple of others as long as it was able to pass through, but it would not be a T. So for a kettle, which we can tell that it's a kettle just from the outside shape, it has a much larger maximum diameter on the body versus the mounting flange for the bundle. So we commonly refer to them as kettles, but it's still a heat exchanger. This weir wall just forces the bundle to actually have a liquid level greater than the bundle. That's the nice thing about these. And they can be used in both heat exchanger and in condenser configuration. Is that important? Well, it can be, but when we're describing it in our reports, if we use the letters that it is a 30 by 120 AKT carbon steel insulated heat exchanger, that goes a long way to describing this exact configuration. You could get in and get geeky about the different tube sheet ligament hole arrangements. Is it a 30 degree, a 60, a 90, a 45 degree orientation on the tube sheet? How many passes is it in the channel? Is it a 2 pass? Is it a 4 pass? Is it a 6 pass? All the different pass partition plates. 31 is the pass partition plate. You could get in and get geeky about, what's the configuration of the channel to tube sheet, and shell to tube sheet configuration. Items 3, 6, and 10. If I described to you that 3 and 6 were drilled, or 3 and 10 were drilled, and 6 was threaded, that would tell you that it's possible to leave the rear bolts on the shell side for the bundle and take off the front channel without disturbing the gasket betwixt the tube sheet and the front shell flange. That would be important. That way you could work on the tube face for whatever reason at the tube sheet without having to pull the entire gasket or try to roll the gasket onto the backside, which allows you to work on the tube sheet face without having to reach through the channel, which is why a lot of times they will thread the tube sheet. A lot of people don't like it because it makes it harder to stab a bundle, and it gives you the chance of damaging the bolt studs in insertion if the bolt studs are still in place. I admit that is a scenario that can happen, but that's why you would want the tube sheet threaded. And if I describe that by listing item number 6 as threaded, that should be very obvious to everyone why that was built that way. Depending on what application the exchanger is in, it may not be something you ever see, but when you do notice it, doesn't hurt to note, and that's an easy way to make that notation just by the component numbers. That way our abbreviations are more uniform across our reports. And that's what we're ultimately after, is being able to be most clear and that way consistently from one report to the next, from one event to the next. When we have original construction drawings available, we should compare them to the previous reports available. Hopefully they match, and if they don't, that we reconcile our report with the original construction drawing and translate the previous. That way they all compare to the same. Anyway, that's a whole separate and maybe confrontational topic, but the thing I wanted to cover today is that there are letter designations from TEMA. They're recognized by code. It's not an ultra geeky way to do it, because it quite honestly, it should be the only way we describe exchangers. With the TEMA group manufacturers, a lot of times you'll see the letter designations on the nameplate. If they're not members of TEMA, then a lot of times those letters aren't on there. But even if they're not on there, you can use these letter types to describe that. And if someone describes to you a CFU, you should be able to either visualize this exchanger or make a drawing that coincides with that. And these letter combinations can be in any configuration. In fact, they have the N and the D down here, and D describes any special high pressure closure. And a lot of people say, oh, you'll never see one of those. I've actually seen a few in my career. Had a chance to see those early on in my career, and at the time everyone was referring to them by where they were manufactured, Kobe, Japan. And that kind of frustrated me, because although that describes where they were made, it doesn't describe anything about the method or configuration of construction. And if we look right here at the TEMA chart, the letter designation delta clearly describes that would be a D-type front head configuration. In fact, that specific exchanger was a DE. Let's see. It was a DET. Yeah, DET. Probably the only time I've ever seen one of those. Those exchangers with that delta type cover were very, very large. They were, goodness, over 4 foot diameter and over 2 foot thick for the cover. Had an Acme type thread that threaded the unstayed cover into place. But the neat thing about that is even 25, 30 years later, the best way to describe those would be a D-type front head configuration that just happened to be manufactured in Kobe, Japan. Anyway, I hope this helps at least one inspector. Maybe the rest of you guys find some use and value and uniformity in this information. If you guys have any questions or comments, please leave them in the comment section. I do read those and review them and respond to them. Drop me an email if you've got a question or a topic that you'd like covered, and I'll work at getting it on the list. Thanks for coming along. Talk to you guys later. Be well.